So now I'm going to prove a different statement about minors. This one is going to be really useful for proofs, especially if you want to prove things about graphs or families of graphs that are closed undertaking minors. Then if we want to especially prove something about graphs with a certain level of connectivity, in this case it's 3 connected, then it's really nice if we can do induction, where we take the graph we have, we contract an edge, and we find that it's still 3 connected, and therefore we can apply induction and hopefully prove it about the original graph that we started with. So the statement of the lemma, to fill in the box here, is that if I have a 3 connected graph, it has at least 5 vertices, then at least some edge in the graph is such that if I contract the edge, the result is 3 connected. Again, why do we care? Because we're going to use this in proofs by induction, and let's be careful. Just draw an example of a graph, and we can see how we're going to have to be careful about which edge we choose, because not every edge will do. Let's give these edges some names. Let's call this A, maybe this one is B, this one is C up here. If I contract the edge AB, so if this is G, and I contract over here, and I take, okay, I want G contracting edge AB, then I can draw the result, right? I have this vertex AB here, C is up here, AB is connected to this last vertex over here, and I still have this vertex and this one. Now you'll notice that this graph that I've drawn, this G with AB contracted, this is not 3 connected. On the other hand, if I were to contract BC, let's see what we get there. If I contract BC, I get a single vertex BC, and I still have A over here, and I have another vertex here, one here, here, and here, and I get K4. And so this one is 3 connected. Okay, so I see, at least in this case, I did have an edge that I could contract that would result in a 3 connected graph, but I've also seen that not every edge that I contract will result in a 3 connected graph. So I'll have to see, how do I guarantee that this one exists, and how do I find it? Okay, but before we do that, we'll warm up with a slightly easier question, which is the same lemma, but for 1 connectivity. So we'll call this warm-up part 1. If G is a connected graph, you can think of that as 1 connected, and there's at least 2 vertices, then any edge you contract, the graph will still be connected. Okay, so if I just took G to G contracting E, might even call this G mod E. If I take that contraction map for any edge E, then I can look at any 2 vertices. Right, so take any A, B in the contracted graph, G mod E, and I know then I can always look at vertices. I could take at least 1 vertex for each A and B from G that maps to A and B. So I can take A prime in the preimage of A, and I can take B prime in the preimage of B, and I know there must be something because it's a contraction, so it's surjective, so there's something in the preimage. And so I take these, and now from A prime to B prime, this is in G, there's a path, or there's at least a walk, let's say. There exists an A prime, B prime walk, right, which is going to be, you know, a map from a homomorphism from pk to g for some k, so a path into the graph, and it starts at A prime, ends at B prime. And since G is connected, that walk has to exist. Such a walk has to exist. And now I claim we're done because F composed W is an AB walk in G mod E. And now for any two vertices in G mod E, I was able to find a walk between them. Therefore, G mod E is connected. Okay, that's the nice, easy warm-up. It seems simple, good to work through it with a little care. And we'll even use this in the proof of the more general statement. But before we get there, we can do warm-up part 2. Let's do this for two connected graphs. If G is two connected, and now I think I need at least, let's say, 4 vertices, then there's some edge, E, there's at least one edge, such that G mod E is two connected. So this is going to be like in the 3 connected case, where we'll have to be careful about which edge we pick. And maybe I will teleport in another piece of paper here for a quick example. Let's take a nice two connected graph like, let's just take a maximal outer planar graph like this. This is a two connected graph. But clearly, if I were to contract this edge, the result would be a graph which is no longer two connected. And I know it's not two connected because I've got a cut vertex. So I can't just choose any edge. I've got to be careful about which edge I contract. If I were, on the other hand, to contract, say, this one, I think I would be okay. I think we would see a graph like this in the result, which continues to be two connected. Okay, so there's some edge I can choose. There's at least one, but I might not hope that I can choose any edge. I may not be able to choose an arbitrary edge to contract. Okay, so let's prove this one. Suppose for contradiction that for every edge in G, if you contract that edge, it's no longer two connected. That somehow there's just not one of these good edges that we're looking for. There just isn't one. Every time you pick an edge and you contract it in G, you always end up with something that's not two connected. So if that was true, then I claim that after you contract that edge, the new vertex you created from that contraction has to be a cut vertex. If the graph is not two connected, it has a cut vertex, and in fact, that one has to be the new vertex created from the edge contraction. So let's just take a look at that. Suppose for all E, G mod E is not two connected. Then let's call this edge contraction, let's say the edge was UV, and we take the contraction which just maps U to V. So I'll write my contractions this way so we can understand it as a map. This is a map on the vertices that maps every vertex to itself except for U, which gets mapped to V. And so that's going to be our edge contraction, and that will result in some graph. I can call it G prime, which is G mod UV, in which V is a cut vertex. Okay, this just gives me a way of knowing the name of the vertex. That's going to be the cut vertex after I did the contraction. Now, what I'll do is I'm going to choose UV, choose this edge to maximize the size of the largest component, the size of the largest component in G prime minus V. So I remove that vertex, and this, you might also think of this G prime minus V, it's the same as just taking G minus U and V. Okay, so I want the largest possible component. So in pictures, let's call that component A. I've got U, I've got V, I've got the edge between them. And if I were to contract that edge and then remove it, or if I just remove it directly, what I get is A, and then some rest of the graph B. And what I'll do next is I'll choose some vertex W. It's going to be a neighbor of V that's in B, right? So it's a neighbor of V that's not in A. All right, and that means that if I took A, and I took A and I included U in it, this is in my original graph G, then I claim that that is connected. It's a connected subgraph of the following graph, G minus VW. Now, if I had contracted VW and removed that, that would, by our supposition here, that would have to also be a disconnected graph. But now what happens is, if I had taken VW instead of UV, I end up with a connected component that's larger than the connected component A, strictly larger. But I chose A to be the largest, right? I chose it to maximize the size. And so choosing a different one would have given me a larger one, which is a contradiction. All right, so that's how I derive a contradiction, just by saying, like, if I chose this one to maximize something, somehow I can still find a bigger one. And so I must have some edge I can contract to keep this 2 connected. All right, that brings us finally to the main event, this lemma about 3 connected graphs. So I want to find a way, I want to find an edge, really, that in any 3 connected graph, I can find this edge and contract it, and I'll stay 3 connected. That is, as long as I had at least 5 vertices. And the proof is going to look a lot like the proof in the 2 connected case. There's just going to be a couple more vertices involved because I need a slightly larger separator. So again, we'll suppose not. Right? Suppose for contradiction that no matter what edge I contract, the resulting graph is not 3 connected. So again, we're going to choose some edge UV in the graph, and now, in order to find a separator, we'll pick a 3rd vertex. Let's call it X, so that we maximize the size of the largest component. So I'm picking these together. So this is like finding a cut set where 2 of the vertices are adjacent, and the result has the largest possible component. But it does have to be a cut set. And let's give it a name. Let's call it A. Largest component A of G minus UVX. You can also think of this, although it's a little bit harder to write, as G contracting UV and then subtracting this combined vertex UV and then X. So if you want to think of it as 2 operations where I contracted the edge and then I removed that contracted vertex plus one other vertex to separate the graph into 2 pieces, then I do this to maximize the size of the largest component. All right, again, in pictures, what do I have then? Here's my component A. This is my largest possible component. I've got U, I've got V, they're adjacent, and I've got X. And these are a separator. So if I remove these, I've got the whole rest of the graph over on the other side. And I must have some edges from each of these vertices into both sets, because otherwise I could get away with an even smaller separator. So there exists some neighbor, let's call it Y, of X that's not an A. If there were no neighbors of X over here, then U and V by themselves would be a separator. So there has to be some edge. And so let's take XY, and XY if we were to have contracted xy instead of uv, and then looked for a third vertex w to make a separator, then, well, we don't know where w is. Maybe one of these is equal to w. Maybe w was over here. We don't know where it is, but x, y, and w separates the graph. And again, we know that because that was our assumption, is that any edge we contract, we end up with a two-connected graph. So it must be that removing that pair plus a third vertex would separate the graph. Now, if we do that, however, something interesting happens, which is that A combined with, well, u and v now, minus where w, which maybe subtracts one of these off again, I claim that this set here, let me put it in parentheses first, this is connected. It's connected in the graph minus x, y, and w. So this was our other separator set. And so hopefully now you see the resemblance to the two-connected proof. And the reason that this is connected is, well, in order for it to be connected, it suffices for us to what? Find paths between every pair of vertices. So for any two vertices in A, because G was 3 connected, I'm going to have, by Menger's theorem, 3 independent paths. And one of them could have contained W, maybe. One of them could have contained X. But if any of them contained Y, then they had to go through V and then back to the other side, and I could have taken a shorter path. And so at least one path, one of those independent paths between every pair of vertices in A has to still be there in G minus XYW. And so this graph is still connected, or this subgraph is still connected. But it's pretty clear now that the size of A union UV minus W must be strictly greater than A. But we chose A to be maximum. That was, it was supposed to be the largest possible connected component. So it was somehow not maximal, which is a contradiction, right? It contradicts exactly our careful choice to maximize the size of that largest component. So there you have it. The three-connected case, again, kind of follows very similar pattern to the two-connected case. And now, when we start talking about planar graphs, we know some important facts about planar graphs, right? Remember that planar three-connected graphs are exactly those for which you know what the cycles look like. That is all this, what the faces look like. We know that the faces are these induced non-separating cycles. And we also know that if you take a maximal planar graph, then you're going to be three-connected. And so that's going to be handy for us now if we want to do induction on planar graphs, especially if we take maximal planar graphs, we can always contract an edge and keep it in that same class of three-connected planar graphs. We'll have to prove that they stay planar, but that'll all be in the next video, so stay tuned.